Welcome to Model 5 Lifetime Data Analysis case study. In this model, you will see application of lifetime data analysis for three critical equipment from process and oil and gas industry in order to facilitate and clarify all theoretical concepts that we saw in the first day of the training. Consider all methodology in steps as part of lifetime data analysis. So let's take a look and see how does it works. The first case will be the heat exchanger. So the critical components in heat exchanger are the tubes. The other parts are very let's say robust parts, and usually the failures that happen in this structure occur in the end of life of cycle. So the tube mostly is the one that we need to replace for a specific range of time. And what is the prediction of the reliability for a heat exchanger? So here we can see a usual lifetime data analysis or data that we get from our FRACAS system. We have the equipment. So here is the tag from the heat exchanger. We have here a component description, and here we look only on the tube. Then, of course, we have a column about describing the failure that such equipment occur along the time, when the repair starts, how and when finish the repair. Then we have the type of maintenance, the cause of the failure, that's the failure mode, the consequence, and which were the solutions. So one of the very important information that we need to have whenever you perform a lifetime data analysis is when the equipment is starting to operate it. And then here we have the dates. So we're starting to calculate the interval of failure. So look on the equipment level. In this case we saw that we have only one component. There will be no difference when you get to the interval of failure in equipment level or we look on components, because in the end we look on only one component. As I explained before, the heat exchanger have also corrosion or internal or external corrosion from these structural parts here, but that's happened in the end of the life. And then of course after this period, when we actually start to have corrosion in the tubes, we expect also to start a process of corrosion in this structural part here. But based on the historical data that we have, we only had failures along this time in the tubes. So it will make no difference when you calculate the interval of failure for each event. That's in the end we consider only one component. That is the tube, and that's very important information. Later on you see what is the impact when we not look deeper in our database and get only the interval of failure. But in this first example you make simple, and that's the simplest case. We see the interval of failures. So the different this time here is the first, and then the different from the second failure. That's we are applying the cleaning and replace of some tubes. We are able to bring such equipment to their state as good as new. Then we get this different interval of failure here. And then of course based on when they start the repair, when they finish the repair, we have the repair time of each equipment, and then we can also use this data to predict the maintainability and see how is the pattern of repair time as a maintainability. So in the end, if we work in predicts the equipment level here, or we even describe the components, we have the same interval of time. And now let's see how does it work by using a software. In this training we are using the Viable Plus from ReliaSoft. That's one of the best software, I would say the best software to perform lifetime data analysis. So let's open the software, lifetime data analysis. We need to go looking for the software is already installed. So we just need to find here the ReliaSoft, and then click on the options that is Viable Plus version 10. Okay, other files that we need to use is the file that have the case information about the case study, and then this file it will be delivered for you. And let's make very simple, just copy and paste the information that you have in Excel in the Viable software. So here you can see the software is opening, and we already have our Excel templates that we have all your case studies. So and have these templates make easier for us to collect the information. So basically what we're going to do in this case is just copy and paste the information that we have here in this table. But let's take a look at the software first. And just click in here. Now the software is open, and that is the template that we have. We need to open a file, create a file, and open the software. So you come out here, click on the file. We already have a possible file in home, but we want to create a new file. So when you click on new, there will open a possibility to open the new file. We give a name of the Model 5 case study 1, and then we need to find out where we save this file. So we just create this file in let's see, inside the one that we already have, the case study. So here we are, and then it's just create, and now the file will open. So the file open, we have a lot of options, analysis. We focus on the main approach for lifetime data analysis, and we go in step by step. You see that's very simple, as I mentioned at the beginning, but the most important part is that you all understand the concept. So here we are. When the software open, there are a lot of different other models and tools that we can use it. We'll focus on the first one, that's Viable Folio. So here we can see that uses for lifetime data analysis is the most commonly used folio in the application. So we also see later on degradation analysis and other methods here, warranty analysis. But let's start step by step and look on the lifetime data analysis. So we click on the next step, and then the next question is what type of data that we have. So we choose complete data. We have time to failures. Here we will select that we want to have as a parameter years, and then of course here the type of data, the failure to data is the question that they ask if we have right sensor data, left sensor data, or data in group, and then this information is based on we discussed in the very beginning of the methodology that's of this training, when we define the statistical basis and concept that we define the type of data. But we are looking on the simplest case, that is complete data. We have exactly data where equipment failed, and that is happen when we have a FRACAS system that collects proper information. So we already define our templates. When we click OK, here in the left side we will open a file, and then here in the center that will be the blanks that you need to input information, and here are all the options and the analysis that you're going to do with the software based on information that we have. So here we are. As I mentioned, we have the folio 1 as a typical folio name, so we can rename. So it's our first step. We're starting with heat exchanger. Let's put case 1 heat exchanger. We are working this equipment level, so that's our file. And here we are copy and paste the historical data, and here we see that we have different PDFs that we can choose, but we, as we mentioned before, we perform what we define the fitness of the fitness test to see which are the best function that fit on the data. So let's start step by step. The next step is to get the data to input it here. So we go to our Excel template and we look on heat exchange. So as I mentioned in study case, let's just improve here. So as mentioned in the study case, we have this first template here with general information about the failures that we have. So it's important if we got the time to failure and the time to repair. So based on this time to failure, as I mentioned before, since we have only the two components, that will not make difference if you get the data from the interval of failures of the tube that's being replaced when the failures happen, or if you get the data from the equipment here, that there's no component described, just an equipment level. So we copy and paste this information here and paste on the viable software. So here we paste the information. So this information all in years. We need to be careful with these parameters here. If we made some mistake or sometimes the software has some default, we just click in here, we will be able to modify the parameters, and if you want some conversion they can do that. But it's not our case. We were careful. We consider that. Here we can put some information about the equipment. Since we have the same equipment, we do not do that. And then we move to the next step. So the next step is to choose here the live distribution, and that is what we call the goodness of fitness test. But to do this goodness of fitness test, we need to look on here the options that we have. So as I described during the training, when we use a rank regression, because the time of the failure is our variable, independent variable, continuous independent variable that we use the rank regression in X, but we also have the options to have rank regression in Y. We can use maximum like LaHood. We can use other methods. So and then of course we will keep here at the first our maximum rank regression. So beside here we also have other methods. So ranking methods to determine failure model orders. We have here median rank, and we have here possibility to define a confidence level. So we have different methods, and the Fisher matrix that's used as well for this methodology. So let's use the rank regression methods, and then see based on the rank regression methods in X which are the PDF that better fits on the data. So the software run the simulation, then here pointed out the number one is the viable tree parameters, the number two is the generalized gamma, and then they have number three logistic and so on. So if you want to apply what the software decides, so is viable tree PDF, we just click on here to implement, and then automatically here will come out viable tree PDFs, and the parameters are calculating here. So as we learned during our analysis, our concept part of the training, we have a beta 2.18, so that means the beta is getting close to 2.5 and then we have approximately a normal PDF. We have the 63% of failures will occur until 1.92 years, but as we have a gamma, this 1.92 years after this 1.6 years. So we have 1.6 years with 100% of reliability. Those are the information that's the PDF defined for us. But we can easily here plot the PDF. So if we click in here, we will be able to check and look on the PDF format. So you can see here that is the viable paper that we also demonstrated during the training. So we got this curve here, and then we approximate for a line. This value here is the gamma parameter, and then we can look on more information here. So the first one is to look on the PDF parameter, and we see that the PDF is skewed to a little bit skewed to the right side, because and then is not a perfect normal PDF, because you see that still the beta is 2.18, is not higher than 2.5, and then we do not have a perfect normal. And but we can see what is the PDF very easily if you look on the failure rate. So we understand if you have increasing failure rate, and that's happened. So we have increasing failure rates from the 1.6 years, where we already have 100% of reliability. So after this time, you have increased failure rate. So that was we also saw during our theoretical part that we need to apply in this case. If we want to perform some inspection, that's a good indicative that we need to perform before this 1.6 years some inspection, some non-destructive tests in the tubes of this heat exchanger to try to detect some information. And then of course you can plot other pictures. You can plot unreliability function that's in the verse of reliability. So here's a cumulative probability of failure. So if we get this let's say 2.8 years, we have here the reliability, and we also able to predict the most important one, that is the reliability. So here is the reliability. We have 1.6 reliability in 100% of reliability in 1.6 year, and then the failure starts to come out, the reliability reduce. Just to demonstrating one important tools that we have here is that we are able to calculate the reliability and other parameters in this electronic calculator. So here is the mission time in 1 year. If I put 1.5, so I will achieve 100% of reliability. So here we are reliability 1.5 years. So here is in year 1.5 years, supposed to be very higher. And yeah, just make a mistake here. Actually, need to put 1.5. So so greater than the gamma, they says that yeah, they do not calculate. But if you put let's put 1.7, they will calculate. Here we are. So close to 1.6, we have approximately 100%, 99.85% of reliability. So and then that's prediction of reliability. If we calculate the probability of failure cumulative, that's the inverse of is the complementary of the reliability. Then for this specific period of time, we can calculate the failure rate. So the failure rate in this time, you can see is starting to be lower. If you calculate the failure rate in 1.5, so they do not calculate because we have the gamma. But if we compare 1.7 with 2, for example, we'll see that 2 is lower, and then it's starting to increase this failure rate. So we can apply such a methodology and make different calculations from different parameters. If you want to calculate the mean life, they gives you is 3.31 years, and other parameters as well. But the most important one is to know the parameter. And if you want to know the specific value of reliability, we can just calculate in here, and then this calculator gives to you, as well as we have these different graphs that give us different information. We can also add graph here. If you can have one for reliability, another one for failure rates, we can have both in here and work with that. So very simple case. In this case, we do not have complication. we are working equipment level, but actually we have the same interval of failures concerning equipment level and component level. So let's move to the second case and see what we have the new in the second case. So let's move to second case. We're talking about now pump. Then again, pump. In our historical data, the pump started to operate in 1990. Then after some period of time, we started to collect failures. And here you can see we have the same pump, but we have different components as such as bearing and seal. That mostly are these two components that we collecting failure during this time. Then similarly, we have the repair time, starting time and finish time. We have a maintenance cause and consequences solution. So if we got basically each information inside the template, we will see that we have concerning the pump here, we need to organize in bearing and seal. So if we organize in bearing and seal, we have the interval of failures of bearing and automatically the seal. But we need to avoid and to do that we need to prepare the template for bearing and the template for seal. What we need to avoid is to have a template with the information of the pump as demonstrated in here. I mean, to calculate the interval of failure based on the mixed time of failure of different components. So the mistake that I need to avoid is to include this column from time to failure here and just calculate the interval between the failures for the equipment level, because you see that here the first one to fail is the bearing, but and then I have the seal, but this seal is not fail after this bearing. It's the interval of failure is this period of time minus this period of time for the seal, and then come out again the bearing. That's why I need to organize this template in if I have components, I need to work on the bearing component to organize the interval of failures, then the bearing, as I did here in this template and did here, and then I put all together in one template if I want to calculate the pump reliability. And then of course I can calculate the pump reliability, the bearing, and the seal. So let's take a look on how does it works in a viable software. And now I'm working, open a new file here. Just came here, open a new file. So I just need to go ahead with my steps. I have the unit in here. I have to time to failure, complete time to failure. Then the template that I've got is the time to failure template, and that will come out in the software. And then again, I need to go back to my Excel templates now in pump, and those are the files that we already discussed. So in this case, I just demonstrating what's the right steps to do that when I know that I have components described in my database here as demonstrated in this file. Then of course I need to organize that. So here, as I mentioned before, I have different times. Sometimes comes the bearing, sometimes the seal. That's mixed. So what I need to do is separate in a template the bearing components and the other templates, the seal components, and then in the end I will have a template organized with the proper time to failure of each one. So and then that is what I've got. But let's start from the beginning. Calculate the pumping bearing. So the pump bearing will have this time to failure. So let's copy and paste for our software. So here we have the folio. We rename. So we can put case study 2 pump bearing, and then I can just copy and paste the data here. With this data I will use my Hanker regression, then I will check which are the PDF that better fits in this data based on the Hanker regression methods. So here we are. I have the exponential 3 parameters as the best PDF, and then the viable one as the second one. So I expect to have a value between 2 and 2.5, 1.1 higher than 1 and below 2.5 for this viable 3 parameters. So yeah, again, if I implement that, I will get C higher than 1 but lower than 2.5. That is the beta, and that's the characteristic for this bearing. So we can see that the eta here is 1.11 until 1 year and 11. We have a 63% of chance to have a failure, and the failures actually do not happen after 1.81, almost 2 years. That is the gamma parameter. So let's take a look on the, and you can see here the whole, that's the coefficient correlation. We also had a chance to look on it, and then you can see that we have a high number, close to 1. That means that though this data is very well applied to these viable 3 parameters. Let's check it now for application of maximum likelihoods. What is the good enough fitness of likelihood? We can also do that. Just demonstrating here, based on likelihood method, we have a normal PDF. The second one is log normal, so I can implement that if I believe that's the best approach. So I get a normal PDF for the bearing. That make more sense in my analysis. And then that's a very important point. Whenever we perform lifetime data analysis, we need to consider our experience in the data. So as long as the bearing have a wear-out phase very characteristic, I consider that the normal PDF would fit better. Then I can apply different methods in here, and then to calculate the mean and the standard deviation. So you see here that will apply the mean and standard deviation. Based on the Hanker regression, it's also possible to make the similar analysis, but the Hanker regression gives us the different parameters in here. And then in order to calculate gamma, he changed that for a nonlinear Hanker regression, just to calculate the gamma parameter. As we already saw, that's the equation do not fit, but we use here, based on our experience, we know that maximum likelihood is the best, give the better results, so we apply the normal PDF. So the normal PDF, now we have mean 2.76 and standard deviation 0.6. So let's say after 1.1 year, the failure rate, we expect that the failure rate is starting to increase. So let's take a look on the bearing pattern of failure. So here is the normal paper with log values in both sides. So here we want to plot the reliability, so we have the reliability curve. So you can see that here, as I mentioned, until 1.1 here we have 100% of reliability. The unreliability will be the inverse of this graph, of course. So the probability of failure until 1.1 year is very low. And if you look on the failure rate, that's very interesting. Based on reliability, it is where we define our inspection. We can see that the point around 1.1 is when the failure rate is starting to increase. So we can check that based on the graphical view. So if we click in here, actually here we can move a little bit the values on the graph and see different values. How does it work? So we have all this property here. We can change the legends, use the legend here, change the labels, the name, and also let's say give another names for the graphs, for the title. So that's not necessary, is already very well done. And of course we can play with different characteristics here. For example, we can look on the graph by itself and check the values, how does it change along the time. That's also very interesting. So here, as I mentioned, you can see here below, when I move my icon here, I see the value of reliability. So as I mentioned before, 1.21, you have 100% of reliability. So after this time, my failure rate is starting to increasing, and then here I have different types of different failure rates. So it's very important characteristic that we can check different values of the graph. So if we could put on reliability, for example, we can check reliability for one specific point in the graph. So for example, if I want to know exactly what's the reliability in 2.5 years, so when I click here, I can see below that I have 70% of reliability. So here will shows up all the value of x-axis and y-axis that I'm working on. So if you look again, you see now below 2.0, and then when I go up, I can see that this value here is 70%, exactly the point that I got the y value 71.4 years. So that's also a very good, useful tool. And of course, I can use here my calculator. So the calculator gives us the possibility to make a lot of calculations. So for example, as I mentioned here, our mean is 2.766. So in the normal PDF, the mean is equal to MTTF. So it's equal to the mean life. So here we are, the mean that we have in the parameter, so is equal to the mean that we have here, MTTF. And then of course here I don't need to plot the graph. I can calculate my reliability along the time. So reliability in 2 years is high. So if I calculate reliability 1 year, will be close to 100%. If I put 0.5, will be higher as well, so close to 100%. And of course the interesting is the failure rate value. So as we have a normal PDF, here we can see I have a very low failure rate until 1 year. So we still have this very low value, and then after 1 year actually it's starting to increase. If I put 1.2, you see that the value is starting to increasing. Yet I have 54, 0.054. If I put 1.4, I will get 75. If I put 8, I will get higher. So after let's say 1.1 year, the failure rate is starting to increase after 1 year. So here you can see in 1 year is very low. If I put 0.9, is very low. So that is the time that I need to perform some inspection in order to detect the failure in the bearing based on reliability data, of course, and then I can take a very good action. So now what I'm going to do, those are the bearings. So here I can also put the date, rename this information here. So made a mistake here, sorry. So I can rename this template, put bearing, and then when I plot, if I want to plot, let's eliminate this plot, and then plotting again. If I plot again, I will see my graphs with the name of bearing, so bearing plot. So it's also make it easier. Here I can, as you mentioned, I can create as much as I want to create templates. So I can create the reliability and create additional templates, of course, additional plots. So, and here I can put rename for bearing, plot of bearing 2, or even reliability, the name that I want to include in here. So this 2 characteristic is very important. Then I can go and create once more. That's another one that's very important, is the PDF. Then to not be lost here, I can put PDF here. Then I have additional name here, so just need to click on the PDF, and then in the PDF you see the perfect shape of the PDF that I have here. Need to be careful with the units in years. So now is in years. You can see when I expect failure. So I have the PDF, I have the failure rate. So here I also need to put in years, and I have my reliability in years. So that's fine in years. Okay, so now just let's do the same for a seal. So I will add a folio. So in here, so they will come out a second folio, and then I will do the same for the seal. So I will rename, I will put case study 2 pump seal. Then what I'm going to do is to go on my template, get information from the seal, just copy and paste, then paste in here, and go again, do now I consider my Hunker regression. I just get the analysis here and see which are the PDF that's better fit. So here we can see that there are information also important here that's concerning the PDF. So here they show me that the generalized gamma is the best PDF and the gumbo is the second one. And here they put information about the error in Viable. Large vector C distribution with the setup. So he did not calculate the Viable tree parameters, but we can use the gumbo or generalized gamma. Then let's just first step implement what we've got here. We calculate the generalized gamma. Then here he used nonlinear Hunker regression to calculate all this parameter. And let's check now in generalized gamma what means when you have these parameters, because as remembering from the theoretical part, the generalized gamma, we need to have a combination of values to define which are the PDF shape. So that's generic PDF, so it's not simple like a Viable. So we need to work on the PDF shape. So the PDF shapes here shows, yeah, the formats of a gumbo that is skewed to the left, a little bit skewed to the left. And that, if you look on the coefficient of correlation, the whole, you have 99.81. So now let's come back in here and just plot, use the second one. So let's just show that the second one is the gumbo. So we have here 9981. If we use Gumbo here, now I can choose the other PDF, apply Gumbo. So we have 98. That's also a high coefficients correlation. So we can use in this case the second option, that's the Gumbo PDF, in our analysis, and that will not be any issue. So let's just change our method here. Use the max likelihood and calculate the rank of PDF. So if you calculate the rank of PDF, you can see that the Gumbo is the first one that's better fits on the data, and then we have viable two parameters. So let's take a look on the viable two parameters now to see which are the Gumbo, and then we if this viable two parameters is very well approximated to a Gumbo, we expect to have a higher value for the beta, the shape parameter, higher than 2.5, higher than 3. So let's see what's get. So here we have the beta, the characteristic life very high, and that's characteristic of the gamma. We can also have a characteristic of the Gumbo. We can also have Gumbo with lower value of the beta, but Gumbo have this characteristic very higher value of the beta. And then when you look on the graphs, the shape parameter of the PDF is still a log normal. If we calculate here, we still have the same log normal. So that's not change anything in the end if we have this beta. And then of course we can use the Gumbo as indicated, the PDF, and that will be our better approximation. So here we are. We see also that the Gumbo, the value of the parameters that you have in Gumbo will be very approximated. Is very similar that we have if you have a rank regression. So here we have 3.39 and 0.47 if you have maximum likelihood. We have 3.37 and 0.36, so very close values. So here we can put still here we can put still PDF. So here when you use the software, that's an advantage. We have the possibility to look on the shape of the graph and understand the patterns of the failure. It's not only to calculate parameters and take conclusion about the parameters. We can look on the graph. That's make very easy our life. So for example, when you have something such as a generalized gamma, we can easily apply the plot graph and see the shape and take a look on different information. So that's the advantage to use a very good software such as this one, Viber++ from ReliSoft. So here what I'm doing, I'm just plotting the reliability. So always be careful with the units that we are using here to not be confused. So just check if we have the same in the PDF. Yeah, here in years, and then now those are the three most important. If I do reliability analysis, I will insert the plot of let's say here is the seal failure rate, and then I can come in here, just change for click on failure rate, and then I have my plot. Then I need to be careful with the units that I'm using. So now it's adjusted. So I can see here that's my failure rate for a seal starting to increase after 2 years, and for a bearing 1 year. So I have 1 year difference. Then I need to do two inspection in this pump, in 1 year for a bearing to check their condition. After in the second year here, I will do the inspection for the seal. And then you can detect the degradation for the seal, as well as the previous case, the degradation for the bearing. So that's a different interval of time, and that's happened because we have different components. If we click on the calculator, so we can just take a look what is the failure rate here for this seal in 2 years. So in 2 years we have, in 1 year we have a high reliability, so we can see in 1,5 still have high reliability. And in case of the bearing, now I'm considering I have a pump, so I have the seal and bearing having different period of time of degradation. So the bearing happened before, so in 1.5 I still have very high reliability, but I have increasing failures in the bearing case. So here, yeah, let's see in 2 years what's the reliability. Still high. So after 2.5 years I started to still have a high reliability, but starting to decrease. So you see in 3 years. But if I look on a failure rate, so just look on the failure rate here, and the failure rate here is let's say 2 points. Failure rate in 2 years actually is low. If you put failure rates 1 year, is much lower, and even in 1.5, that's the period of time that I have in the bearing. So now we are assessing this. So you can see that 1.5 is still having lower failure. Then some people can ask to optimize in the inspection preventive maintenance time. So maybe sometimes come out some suggestion to do the both equipment inspection in the same time and do not have a shutdown of the equipment twice. But if I do the inspection in the seal, the failure rate is very low. In 1 year is very low. So that indicates that probably I will not detect any degradation in the seal. So in this case I need to do 2 inspections in 2 different periods of time. So then now what I'm going to do is to demonstrate the pump PDF. So now that I have the clear idea about the 2 components, I will calculate the PDF for a pump. So I open a new folio here, and then I will calculate the pump PDF. And then basically what I'm going to do first, I will rename. So we have a case study 2, and then I put pump, just pump. Now I need to get the data from the bearing, so just click on bearing, come in the data, and copy and paste. And put on the pump. I can work on here as well, that is make it faster. And I come to seal, copy and paste the data from the seal. And I have all the information related. So it's very important that you see that I first put the information concerning bearing, and then the seal, and this data is not in the order sequence in relating time. So here I have 2.12, and after I have 2.2. So but when I click on the wizard here, such data is automatically organized in sequence, in order from the smaller number to the higher number automatically. Now I can make the goodness of fitness test and assess the height of my PDF. So here I have generalized gamma and variable tree parameter again based on Hankel regression, and of course if I change for max likelihood, I will have probably different assessment analysis Then I have gumbo as the first variable, 2 parameters as the second one, and normal as a 3. So for me, as us experts in pumps, I see that this maximum likelihood make more sense for me, since the normal PDF comes in the third, and probably the gumbo comes in the first case. So I just implement to see the information that we have. So we have a gumbo with 3.26 and some degree 0.47. And the likelihood, that's a very important also information that we saw during our conceptual, the theoretical part. That's the likelihood is minus 9.94. So that is, if I look on the normal, for example, I will have lower likelihood. So if I just change here for the normal PDF, so the value will be lower than this 9.1. So you see minus 10.21. So this value is lower than the gumbo. That's why in the goodness of fitness test, this information shows that this PDF here, the gumbo is the best one. And we can also have the generalized gamma. So another PDF, if I calculate the parameters, let's see the value of the likelihood function, so it's even lower. So that is the best PDF. So let's get this example here, and let's check what is the value of the shape of the parameters. So now we are working as a pump. So just include here the pump name. Great. So now we want to look on the shape of the data. We put pump PDF. Because we have a generalized gamma, actually it's hard to see which are the parameters. So just calculate the PDF plot, and now you'll see the shape. So this shape you can see is something like a gumbo, but it's not a perfect gumbo. You can see that's the line here drop below. But as we saw, that's the gumbo and the generalized gamma are the two PDFs that have the best value. So I'm going to use the gumbo one. So if I have the gumbo one, I will have, of course, a mean and standard deviation from the gumbo. I know that the PDF is skewed to the left, and now I will have a better format if I click here on the shape, but it still have a shape of the gumbo. Then I see that is skewed to the left. So that this PDF format shows that I had the influence of the fillers from the fill is higher compared to the influence of the bearing, and some of the bearing also happen after 2 years. That's why I have still some failures from the bearing happen in the very beginning, but most of failures of the bearing still happen after that. That's why I have this gumbo PDF and skewed to the left side. Okay, and then again I can insert different plots here, and then I will put pump reliability. Pump reliability. So here always look on the time that you have, and then you see that we can easily get such reports, such graphs here, and use it in a specific report. So it's not a big issue, it's very easy. And actually the graph shows too much, gives you a very easy information about what we want to predict. And then let's take a look on the failure rate. So that's a very interesting, important issue. So if I look on the failure rate, so I see that that's consider the seal characteristic that I need to make some inspection between close before 2 years. But here we see that the failure rate in 1.2 is still lower, and then the failure rate started to increase after 2 points, let's say 3, 4. So if we look on our values, the different values, we can use here our calculator to do that. So let's use the calculator to calculate the failure rate in 1 year. So we have the failure rate in 1 year, low value. So we have the failure rate in 1.2 is still low, and we have the failure rate in 1.5. So it's starting to increase, and the failure rate in 1 year is very low. But if we compare with the bearing, and the bearing will have definitely a better result. So if we just come back to the bearing and calculate the failure rate in 1 year, here we have 0.018, and then in 1.2 we have 0.038. So come back to the pump. If I look to the pump and go to calculator, here I have in 1 year 0.17, and 1.2 years I will have 0.26. So here, if I look on the pump in general, they're telling me to do such inspection later than if I look on the bearing, and that's maybe is a dangerous point. So what I'm trying to demonstrate here, that if I have the data in an equipment level, I just do some inspection the pump in 1 year, and then of course based on my experience I know that the equipment that expect to have some failures are the bearing and the seal. I will look on all equipment, but especially for the bearing and seal. And then if I do not detect any failure in the seal, if I have not the picture of the components and I do not have the data in my this specific definition of components in my database, I just do some inspection in the 1.2 1 year, and then I will wait for more, let's say 1 year to do another inspection, and then probably that's a very dangerous game. When I look for different components, I can see for specific components when I need to do inspection, what's the characteristics and patterns of the failure along the time, as well as the reliability. So I define that in the case study, in the theoretical parts, that when we look on equipment performance, if we are able to depict such equipment database in components level and look also prepare the PDF in components level, that's the best case scenario. But that depends on the data, how is the organize our data. That's why we discussion that in this two FRACAS model. That's very important to have a good FRACAS that enable us to put at least in level 2 in the component level the data, and then whenever we have more than 3 dates, so that we have in here in this case studies for seal and for bearing, we have more than 3 dates that we can predict some PDF, and then we can start to have some better prediction in components level. And that's very good for a maintenance group to look on components level and have different strategy, different inspection time for different components. Then of course if we have more data, we can go deeper in failure modes, but if we have already components, is very good database actually. So now let's move to the case study 3. So case study number 3. Now we're going to assess the screw compressor. We apply lifetime data analysis. So as the previous case, we have the initial template. Here the first column we have the compressor that we are assessing along the time. Here the time where this compressor is starting to operate. Very important information. You have your 0 time as a reference, and here you see a column with different components. Here we see the failure date where such a compressor failed, then repair and repair start and when repair finish, then maintenance type, cause, consequence, solution. So usually is all the information that will come out from our FRACAS. Then again we go through that to perform our lifetime data analysis. So here in this template, as we always do, we need to define the time to the failure and time to repair. So what we are seeing here is that if we do not have the components, we just consider this starting time and see the difference from the first failure to the starting time, and then the second failure for first failure of the compressor, and then we have this time here. So, but you need to be aware in this case that we have components, and then we are making a mistake in doing this approach, because see here in the first case is correct. Okay, this time to fail is correct because the bearing was the first component to fail, so we just get the difference between this date and this date, that's 2.46 years. But when we go to seal, we cannot get the difference from this date to this date, because the seal also started operating in 1 January 1991, so I need to get the difference from this age to this age. Therefore, I need to organize when I work, even if I want to predict the lifetime data analysis, and the first step is to define the time to failure interval, I need to organize components by components in here. That means I will do the seal templates, and then of course the seal templates is correct because I get the first date that I have the failure in the seal, but consider the starting point here, and that gives me 3.15, and then the second one, the difference between these two, that's 3 years, the difference between 2.89, and so on. And then I need to do the same that I've done for seal. I will going to do it for the cylinder. You see here the first time that the cylinder failed is this one, so I reduced this date for this one. I got 3.86 years, and then I go doing the sequence of the time to failure for the cylinder. The second failure is in 98, so I get the difference these two and get 4.0, and so on. Then I go move forwards, do the same for the valve of the compressor. Get the first time that failed was December 1995. Get the difference for 991, so I get here 4.97, and then I do the same for the second failure of the valve in this compressor. 998 minus 995, I get 3, and so on. So that is the approach that we need to do for to predict the reliability for screw compressor in equipment level, as well as to look on each component level. And then the next step, I go do the same approach for the bearing. So here is the first date that we have the first failure in the bearing, so I reduce from the starting point, gets the time to failure. So the second bearing fail in 995, I reduce for this date, get 2.9. The same approach, and go to the shaft. The shaft, I have only 3 dates, 3 failure data. The shaft failure 3 times, and then again I get these 3 values: 997, 991, 2003 minus this 997. The failure is different between the 2 dates, and I get 5.8, and so on. And then in the end, I can aggregate such interval of failures of each one of these components that I have in here, to calculate the proper interval of failures for the compressor. So in the end, if I want to get the proper interval of failures, so I need to organize my templates based on each component that I've got. So you have the time to interval of failure. That's we have the seal, the cylinder, the valves, and bearing, and other components. Then of course, if I look on the date of the failure, that's not organized in order, but that's not important because to perform the lifetime data analysis in the equipment level, I need to have the proper interval of failures that failure happened. Then, as we saw before, when I input this data on the software by itself will use such value and put in order. So let's see how does it works in the viable software. So I just starting here, open a new file. So the new file will be, I need to put a name, so it's model 5 lifetime data analysis, case 3 screw compressor. And then now I already have a place here. Then I will create the file. So what the software asks, if I want to create a new one, I need to close the previous file that was open, that was the pump. So I accept that, and now the software will create. And then we go to the similar steps that we had before. We just define as our model the standard folio for complete data. Then we click on, we have the time in years. We click OK. He will open. Then we can start our case study for screw compressor. So you open a file. Now is opening. So you can see that's the year is already in. The time is already in here. So I just put here the model 5 case study 3 compressor, or just make simple. Let's put don't need to put model 5, just put case study 3 compressor. And then now let's do some interesting exercise in here. We go to the Excel sheets, and then we work on the compressor level. So here we have this template that's we are not considering. Look on the components. The components that we have in the compressor just get an interval of failure. So we got this value here, and then we'll see later on the problem that we have by doing that. So we have this data here. We just copy and paste in our templates, and then we proceed with the lifetime, the goodness of fitness test. So we are choosing the Hankel regression. So we are always you can see that we are always choose. We can choose the method, the good enough fitness method that we applying here. The basically difference from maximum likelihood is that maximum likelihood can be applied for all type of functions, but is better. Their result is much better when you have more high quantities of data. If you have a small quantity of data, the Hankel regression next is the best approach, because of course is a linearization of every function. So in the line you need to have at least 2 points to have a line. In case of lifetime data analysis, of course we need to have at least 3 points and more. As much as points we have, better will be our prediction as parts of reliability statistics concept. But we need also to be aware that's not always the case. If you have a reliable equipment component, you do not have too much data. But we need to be here. I just explaining the difference, basic difference that we have in terms of mathematics between a rank regression and maximum likelihood. And of course, as I mentioned before, the experience of the specialist, the expert, needs also to be taken into account. That means even if I do not have a high quantity of data, and if I compare the two methods, rank regression and max likelihood, and believe that the result from maximum likelihood is the better one that represents my failure pattern of such equipment or components, I need to use that. So let's go ahead, use the rank regression and see which are the function that's better fit in this data. So here we have a generalized gamma, vibrate 3 parameters, variable tree parameters. So let's just implement generalized gamma and see what we've got. So here they use nonlinear rank regression, then they approximate the parameters. So here we can see that by the parameters I expect to have an asymptotic value for this PDF. And then here we already have the paper of generalized gamma that will define the parameters. But let's take a look on the PDF. In the PDF we demonstrate that we have a very failures happen along the time here, but concentrate in the very beginning. So let's it's not clear for us what's the pattern of failure. So because it's not clear, what we're going to do is to apply the second PDF. So let's delete this sheet and create again to come, or let's do something better. Let's put screw compressor PDF. So here we are, yeah, and that's the resolution. But just take a look on what we've got from let's move to rank regression again. So the software do not approximate for. Now we have rank regression just to check which are the second one option. The second one is viable tree parameters. So let's take a look on the viable tree parameters. That's what the results that we've got. So again, viable tree parameter, they just use the nonlinear regression because our tree parameters. And here we have the issues that we have gamma, negative gamma. As I mentioned before, when we have a negative gamma means that the failure is starting to begin even before the time 0. And that is hard to explain for other specialists. So here with the shape we have clear characteristic of log normal. You can see that the beta is lower than 1, higher than 1, between 1 and 2, and then shows that most of failure happened at the very beginning here. But we have this negative value. So what we can do in this case, we can take a look on maximum likelihood, what's the result we get from maximum likelihood. So we go again, run our goodness of fit test, then we get generalized gamma, again the viable tree parameters. Then we have viable tree, two parameters here as the third one. So let's take a look on viable 2 parameters. That is very approximately result that we have from viable 2 parameters. So you can see here the viable 2 parameters. We have beta equal to 1.42 and eta 1.07. If you use the viable 3 parameters and calculate. Now we have 1.75 and we have eta equal to 1.4. So is almost the same value. Important here, of course, the beta is still a log normal. So from 1.5 to 1.7 is still a log normal. That's not influenced. And the eta is the most important. That's the 63% of failure do not hedge too much, but it's still 1.24, 1.1 is this very approximately. And if you look on the likelihood value from the viable 2 parameters from the viable 3 parameters is almost the same that we have. So here -20, so we can use viable 2 parameters. Then now we look on the PDF shape of the parameters, so that we had before with viable 3 parameters. Now if we click and plot again, we will have see now the better definition. We have no negative values on the gamma, and you have a log normal. So this screw compressor, actually, let's just to rename here, is screw compressor 1. That is the case that we did not consider the components interval. So now let's go and assess components by components that we have in our template. So I will add one template here, and then what we are going to do is to look on the component and then build this template with the components organized by components. This one here that we want to achieve, organized for different components that we have in the compress. So we need to organize our templates and look on components by components. So this template is the one that we already implement, the lifetime data analysis. But now what we're going to do is to get each component. So we start to do for seal. So here we are. So we go to do for the first component our lifetime data analysis. The first component is the seal. So we just open our template in here. So it's opening, and then we can rename for case study 3 seal. And then of course we have now just paste here all the time. So now we have not too much data here, so we use a rank regression for our goodness of fitness test to see which are the best function for these dates. And then we have variable 3 parameters and generalized gamma and exponential 2 parameters. So we implement variable 3 parameters. Let's see what we've got from the gamma. We have gamma 2.9, we have beta equal to 0.558, that we have here asymptotic shape. So just put here seal, and then we plot, and we see that the failures are very close to the very beginning life periods, but happen after actually happen after 2.9. So we still have a range of data of 2.9. So here is just the plot. We need to that is the real points, and then we translate to the line when you use a plot method, but it always comes out. And here is the density functions that we've got from the variable 3 parameters for the seal. So here actually we see, if you look on it, is not a point that's is not clear what we got. We have 2.9 as a gamma, so after 2.9 we start to get the failures very close to the beginning. So if we are applying, for example, here a variable 2 PDF, maybe we can see that. So if you look on the variable 3 parameters, we still have a very low beta. So here we actually have a very high beta value if you apply variable 3 parameters. So it's not a good approximation. Here we cannot compare these three equations. So because of that, we keep our variable 3 parameters in here. We keep our plots. The failures start in the very beginning. So this is actually, let's rename PDF. So we are now adding, let's take a look on what's happened with the failure rate and the reliability along the time. So we have high reliability for 2.9 time of 2.9 years, and that's a very important characteristic. So let's put seal reliability. So that's in the end is the most important functions. We need just to understand the pattern of failures that we have. So here we are. We let's put it in years. So for you have a clear understanding now. You can see we have 100% of reliability until 2.9 years, and then the reliability drop out for lower values. And then of course I can still insert some here we can insert some let's say plot to predict the failure rate. So the failure rate, let's see how failure rate, seal failure rate, seal failure rate. So let's put in years here, and let's see what's the pattern of the seal failure rate, what we've got. So yeah, the failure rate is there's no failure some specific period of time, and then of course, as we have at this asymptotic failure, the failure is starting in very high level and then decrease and then go to achieve after some point the useful-ize. One important issue when you applying the data is that the assessment, the data that we have is only still 4.09. So we have information that is around here. So the other is almost this line here is just the prediction of the PDF. We don't really have information about this time. So that means as long as we repair these issues that make the failure sign to the high level of failure rates the beginning and in this time here, and get more information actually after 4 years, maybe the PDF shape of the seal change, and of course we get more data. So now let's go ahead, let's move to the next one. Let's including different components now. So what we've got now is the cylinder. Cylinder, we have more time, so we get the time to failure. So I got all the data that I have in the complete template, and now I am assess only the cylinder. So I come back to my software and we'll do the cylinder analysis. Then that's the same procedure and the same lifetime data analysis steps. So now I need to include in here rename for case study 3 cylinder. I will include the data in here, just paste. So I think that I did not got all the data. Now I've got it. I've got all the data. Okay, I've got all the cylinder data. And then I will perform my goodness of fitness test. Here we are. Then again, he gave me a log normal or 3D exponential. So if I implement that, let's see here what this software going to lose. He choose the log normal. And log normal here, this value we need to understand that log mean is including here in order to understand the values of parameters. Then the failures are happening in the beginning of the life period, so need to put here cylinder, and then now I will look on the parameter shape and the PDF shape, and I will see the failures. The shape is skewed to the right side, and failures are concentrating in the beginning of life cycle. So that's what we hear here. It's a little bit skewed to the left, but it's fine. We will have our PDF here. Just change the name, PDF cylinder, and now I will include the RPDF. I will include one plot that is the reliability, the most important one. That is the reliability. I will put the name reliability cylinder, and then I will also include one plot that I want to assess, that is failure rate, and then check it. The failure rate is also we assume that is starting to increasing along the time. So is usual failure rate for log normal. So that means you see that it's starting to increase, and after some action starting to decrease. Just be careful to put the year in here to have time in here. And as I mentioned before, I do not have this time here. Just have the period that the failure rate starts to increase. But as long as I have a function, the software predicts the time ahead. And then of course here, if you, it's just to have the better vision of the time. But if you look here in years, I have 100 years. So if you don't want to look on it, just put my cycle of periods. Then I can change here also, manipulate the graphics value, and then I see what we expected now is that we have only increasing failure rate. So based on, and that's just extrapolation of the data, because it's an equation in the end that we have, but the certain that I have is until the 5.16 year. So let's move forward. Now I will add another folio because we have another component. So that's the usual procedure that we have in here. And then now I get the next component, that is the valve. So if I get the valve in here, I'm just waiting to get the new templates. Then when I get the new templates comes out, I will include in the valves. Yes, it's coming here, so it will appear in this side. And then I will paste, just put the name here. I will rename case study 3 valve. Then I put the name in here in years. That is the valve that I have, and just make time doing the same. Let's put valve here. Okay, so again I will go through my goodness of fitness test to see what is happening with the valve. So they tell me the best PDF is generalized gamma or 2-parameter exponential or variable 3 parameters. So let's take a look, ask them to implement. Let's see what we've got. So generalized gamma and 2-parameter exponential, they gave me generalized gamma, but I have the same value of her if I use variable exponential 2 parameters. So let's take a look on exponential 2 parameters. As I mentioned before as well, you need to look on the PDF that's easier for you to explain to other experts, as well as the one that is easier to look on. So the variable 2 parameters, we see that there's no failure until 2 years. Is that what we have in the data? And after 2 years, that's the gamma value, 100% reliability in 2 years. And then we have this mean time to failure, 1.2 after 2 years. So if you just plot the PDF, we will see the format that's the usual format that we have for exponential, but with a range of 2.07. So here we are. That's the usual pattern of failure of the PDF that we already discussed in the theoretical part of the training. So there's any specific period of time that we have failures, but we have here a gamma of 2.0 something that we have no failure. So that's the PDF. We can go ahead and plot the reliability. So we have 100% of reliability for the value of the gamma. So we put only here reliability for the valve. So here just put a simple case of valve, but you know that in compressor we have inlet valve, outlet valve. It can be one of these valve, of course. We need to specify which valve we are talking about. But here I just put valve to be easier to not go through the discussion. Just here we have our time in years to make it simple. And then we see we have this gamma here, the value that we have 100% of reliability until this 2.04 time, and then the reliability dropped. And then we also can have the failure rate, and the failure rate will be a constant line along the time, but with the gap of this 2.04. So if you put here failure rate valve, we'll see that. So let's just plot the failure rate. So here we have a constant failure rate as we got from all exponential. The only difference that we have this gap of the time that's related to the gamma parameter. So it's very simple to understand what's happening with the valve. And in the end, what we saw so far is that we have different patterns of failure for these three components. Then each pattern of failure requires a different approach to look upon it. So in this case that we have exponential PDF, we do not have any failures in any specific period of time. We cannot look on a specific period of time. So what we can do in this case is to look on the reliability function, and based on the point that we achieve, we need to specify specific targets. For example, between 60% and 80% is a good time that you do not expect to have too much failure. But even here you already have a failure before 3 years. So what we can do in this valve is in this exactly time here, before failures happen, we can establish as an inspection and test the valve, because it's random. We don't know how the real time, but we can see based on the reliability. After this time, the reliability is starting to decrease very fast. So we can establish this time based on reliability, or even some reliability targets here that we expect after this time. As reliability going down, the failure is starting to happen. As we want to be preventive, we can define such approach to detect failure. Okay, so now let's move for the next component. We add a follow here, is the same procedure, and then we get the next component that is the bearing. So we have this bearing date in here. Then now we go back to our software, rival software, then we input the data. So then we see the patterns of failure of bearing. And then now we can see that's the advantage that we have when we are looking on each equipment historical data by itself, because we can see different patterns of failure, time period of failure, and then we can have different strategy and actions to avoid this failure. So case study 3, bearing. So to be honest, the seal and the cylinder, as long as they have early life failure, some problems in design or operation can affect this equipment. Then I need to take a look on the dates that are influence this equipment to have such pattern of failure in early life and eliminate that. In my strategy of maintenance, I do not consider that you have a log normal, or even if I use this database for a prediction, in a run analysis, in our analysis, I will not use that, and then I need to be careful with that as well. So let's go for our goodness of fitness test based on Hank regression. So here they tell us that the viable tree parameter is the best one. Then we have generalized gamma. So just implementing that, so and see what we've got from the result. Yeah, we have a gamma 1.82, so 100% of reliability until 1.82. Then after 1.82, let's say until 3.1, we have 60% of failure. Consider that until 1.8 we do not have failure, and the failures will happen as soon as this value pass 1.82. So we expect here to have a PDF that's is a asymptotic failure. Failure happens in the very beginning of life cycle, but after the 1 year, the 1.82 period of time. So here we are. We have the bearing. Just correct here. We have the bearing. Then we go to plot the PDF. We go to plot the PDF of the bearing. Then we go to plot the reliability, the failure rates, and to look upon these dates in here. And here are the PDFs. That's a very good case. To demonstrate that it's not always that we have a very clear patterns of failure that we can use and work with. So here is the PDF. As I mentioned, failure are very asymptotic, and after we have this 1.82, so something here that we have 100% of reliability, and after that we have the failures will start to happen very fast, and that is the patterns of failure. So we can go ahead and plot the reliability function and the failure rates and see what we've got. So let's plot the reliability function. So there will be a period that's 1.5 with 100% of reliability, and after that we get a very fast decreasing of the failures. So if we put each adjust here for 20 years of the failures, now that's what we've got. That's reliability function. So yeah, until this 2 years or 1.82 we have 100% of reliability. Then reliability goes down very fast, and that is the reliability. And now we'll plot the failure rates. And then, of course, if the specialists need to take a look on it and see if it really makes sense about all this pattern. And then again, one of the very important issue is the database, the root cause, and then that's why we need a FRACAS to understand as well what is behind for this pattern of failures. So let's take a look on the failure rate. So the failure rate is decreasing, and then gets to the useful life periods. So definitely we have something a log normal approach. So now we put in here. So that is the failure rate. Then again, another component that have failures happen in the very beginning. We need to look upon that to understand. So let's move to the next component. Let's add a new folio in here, and let's copy and paste this one that have 3 dates. So when you have a small number of dates, we need to be careful because we do not have enough data to define a trend of the data, the pattern of failures, if the failures happen in the very beginning or not. And then we need to be careful with that. So here we are, our historical data. We just rename here. You just look on which component we're working now. Okay, it's the shaft. So we just rename here shaft, and we paste the data here. And then, of course, now we need, as I mentioned before, that will make a difference when we calculate the goodness of fitness test that we choose. As I mentioned before, the maximum likelihood is better, gives you better result when you have higher quantity of data. When you have a low number of data, it's better to use the Hanker regression. So I expect to have here an exponential as a result, because we do not have too much data, but we got here Gumbo and generalized Gumbo. So even though they put such a Gumbo as a PDF, so let's take a look on this pattern. So and that's good, because in the past, whenever we had some data, we were not able to implement that. The solution that they gave is always the exponential. When we have small number of data, maybe 2 data, they will give an exponential. So the rank regression work with 2 data. So here we have possible error that was not converged for the solution, and that's about the Fisher matrix combined to the Fisher matrix for the confidence level. What we've got here is we need to go again to the main plot and use the Gumbo, and now we got the Gumbo and try to model that. And now we've got our Gumbo with mean and standard deviation, so that makes sense for us, and that we just put here shaft. And now we can plot the PDF. We expect is skewed to the right side, to the left side. That is the characteristic of the Gumbo PDF. So and then we finish with okay. So we can see that we have different patterns of failure for each component. So that's the advantage that we have to assess in components level. So here we have the Gumbo skewed to the left. Let's just put here shaft PDF. So this is the only one so far that I can make some definition of patterns of failures, and the failure rate is increasing, and I can define some inspection time to have some preventive maintenance to detect some failures, degradation that's in the shaft. That's I can implement that. The other case, seal, cylinder are all, and bearing are all failures that happen in the very beginning. They have early life characteristics. I need to investigate that. And the valve is constant failure rates. I need to take decision based on reliability. So let's move on and plot another graph. So we have here in this case, we need to plot the reliability. Of course, the reliability is very high from the very beginning time and the first 3 years, and then it's starting to decrease. That we expect to get from this graph is there. Here we are just putting years to make more sense for us. So here we have high reliability until let's say 3 years, and then reliability is starting to decrease. That is reliability shaft. That is reliability shaft, and that's great. And then now we just put one more, insert one data that is the let's say the failure rates. That's the 3 very important case that we have for our analysis. And then here we can see after 3 years the failure rate start to increase. Here is a classical case that we can really, despite a small number of data, we can see that is a very clear result that we've got in terms of to use for preventive maintenance inspection. We have exactly the time that the failure rate is starting to increase, and then we can define that at least for our first inspection. Then, of course, we maintenance engineers have another method such as predictive, online monitoring, prognostic health management that even define the new expect time to failure, and then the remaining useful life, and then based on it, you can always update the special interval of 3 years. But based on reliability, we got this value, and now we create our next following this case. That is also compressor 2. So we create now compressor 2, but the compressor 2 will get the information from all these PDFs here, and we compare both. So this case now, we are not taking the mistake that we've done before. That's just not look on the components, and that's happened if we in our database we do not have definition components level, just look on equipment level, and that gets an interval between the failures of the equipment level. And then, of course, these reliabilities will probably be very different from the usual case, the real case, the best case, when we have information about the components. So case study, compressor 2, and then now we compare the two reliability. So now what we're going to do, we get from the seal, we get all this data, historical data from that we have here. So we come to the seal. That's are the real interval of failures that we have for a compressor. Okay, so we get the seal data, we copy and paste in the last equipment, and we do the same for the other components. And then now what I'm doing is to use the real interval of failures that happens inside the compressor, in the compressor. And that, of course, is only possible to know if we have our database, our FRACAS defined in components level. So if we do not have that, we do not know the real interval of failures, and then we can make a big mistake by using the data only for, let's say, for based on equipment level. That will be very pessimistic, because sometimes you get interval between different components failure because you look on a compressor level, and that's not the case. That's not the proper approach to do that. So here we input the second data that's from the valve, then we do that again for the bearing and for a shaft. So now I'm not sure if I got the data from the cylinder, just checking here which are the data from the cylinder. No, I did not get the data from the cylinder. So let's do that. Let's get one by one. So what I'm doing now is just building the database for my components. Pay attention here, that is not matter if I put here below or here above, because in the end the data will organize everything in here automatically. But just to be for your clear understanding, I just put in sequence, and you see when I click on the good enough fitness test button, the data will be organized automatically. So now I will get the data. We have actually 5 components, and then we need to organize this data. So this is the third one. Now I'm pasting the valve data here. So here we are. Then now I'm doing the same for the bearing. Copy and paste the bearing data here. And then in the end I will have all information that I need and I just show what is the proper compressor and reliability prediction. And when I see proper, I would like to reinforce that proper if you have components data, because if you do not have, you do as we did as the very beginning of the case study here, that we just plot the interval of data that we saw in the historical data, and then we have actually very different values. So here we are. Now the last one is the shaft. Just need to come back to this template that we have historical data of the shaft, and then I will copy and paste the shaft information, and then that will be done. So here we are, only 3 dates. We need to copy and paste here this 3 information. A very important point that you need to observe as bigger as the file, and if you have, of course, a lot of files open in your computer, the software gets slow to give you the information and to process the information. Actually, this software is very fast, but as all software that you use, if you have a lot of templates, other softwares open, and if you're trying to populate this software with too much information, yeah, that's getting a little bit slow. But you need to be smart. I'm just doing that because, yeah, let's say I would like to show step by step what I'm doing. Next case, I just copied from the templates, but now you need to understand what we are doing. So let's use the rank regression here. Here we have a lot of data. We can also use actually the maximum likelihood, but let's use this rank regression. You see that now when I click on rank regression, the data is organized in order of occurrence. Now I got generalized gamma and 2 exponential PDFs. So again, here I can look on other methods such as maximum likelihood and perform the same results. And as I have some more data, I expect that I have a good result from the maximum likelihood. So just let's take a look what we've got in here from the maximum likelihood, and then plot this information. So here we are. Now we proceed with our test, and we have not different results. We have G gamma and exponential, and that makes sense because now we have different data from different sources with different patterns of such different equipment. So we have equipment that have fails in the very beginning in different period of time, such as seal and cylinder. We have random failures in the valve. We have failures that happen also in the beginning of life cycle for a bearing, and we have failures that happen in the end. So when we mix all this pattern, we expect to have an exponential PDF, but we have some here some gamma 2 parameters, and then the gamma shows that there is a specific period of time that we do not expect failure. So let's use the exponential PDF 2 parameters, and then let's compare both reliability functions. So here we are. So what the gamma says is that we have 1.83%, 1.83 until 1.3 years we have 100% of reliability. And then as we look on the compressor, as we use exponential PDF, so we do not get any trends of failure, and that is one of very important issues of when we assess such equipment. So the result of the exponential is because we have different patterns of failure in these components, and we mix up everything to predict the reliability compressor level. So we need to understand that when we are preparing lifetime data analysis for a database or for a run analysis, we are not considering early life failures. We use that to avoid this problem in our system, but we do not expect that to happen again in a new project. So that needs to be very clear. Actually, such equipment, we expect such seal, cylinder, valve, and bearing, all of them we expect some increasing failures. So that will actually happen if you look on such equipment later on at the time, along the life cycle. But in this case here, case 3, we got data from the beginning of life cycle, then we had problem with such very early phases, some of these equipment such as seal, cylinder, and bearing. That's influence on the PDF. But even though that is the results that we've got, and other point that we have gamma in all these parameters in here, so the failures actually do not happen in the very beginning, but we have some reliability until a period of time. And then for some reason the failure is starting to decreasing a lot, and mostly that's happened for some operator or human error after maintenance or repair or during operation that make the failures starting to happen very fast, and then we need to look on it. And then here I just plot the reliability function. So let's go to plot some reliability functions in here. And then let's compare. Now what I want to do now is to compare the cases, the compressor 1 with the compressor 2. So just let's plot the reliability versus time. So and just need to put in years is in years. So let's put compressor 2 reliability, and then just let's put some 20 years. That's our operation. So let's plot it again. Yeah, that's the reliability. If we plot the PDF, we'll see. Let's just do the exercise in here. If I plot the PDF as an exponential, 2 parameters, so the parameter we do not have any patterns of failure in the PDF, but we have the range of time of 1.8 years. So is that here we are? Let's just put in years. So that is the PDF compressor 2. And we got the failure rates. We will have constant failure rates for sure with a range of time in this PDF. So that's what we've got in this graphic here. So just put, yeah, so let's come back to the PDF for here. Let's create one graph with failure rates. So just to confirm and just for learning process, how does it works, the PDF, the reliability, and the failure rate function. So here we are, now we are creating failure rate compressor 2, and that's a type of analysis that will not give too much information when we assess. We want to take some decision about such equipment. If we use this PDF in a lifetime data analysis, in the run analysis to model a system and put just the parameter of this exponential, that will, in the end, will reflect the reality. We have this run of failures happening, and that will encompass, in the end, the total number of failures that we have here for each one of pattern. But if I want to take some actions, look on the patterns of failure to have a preventive actions to recover such components, I need to have data in components level. So here, just put the failure rate in years, and then you see the constant failure rate, and in some 8.82 years the time that we do not have failure. Now, what I want to do is to compare these two reliabilities. So compressor 2 with compressor 1. And let's see what we've got from here. So I want to compare two graphs. So I click here in multiplot overlap two graphs, and then that's come out a window that's asking me for to choose. So I have a case, I have a bearing here, I have different options now: cylinder, seal, shaft, valve, and then I have here the two compressors. That's what I want to compare. Then when I select these two, I will get the graph of these two, and then that's coming reliability. So that's very important to show how my my decision is influenced based on the data. So the black line here that we have, the blue line is the compressor 2. So this is the reliability of the compressor 2. This is the reliability that I predicted in the first case. So that's the difference and the mistake that I will commit when I do not have a proper information concerning the equipment and consider just the interval of the data that I have. So my prediction of reliability is very low. So here, for example, if I predict the reliability for a specific period of time and have a target of 2 years, and based on this approach, I will tell that is not achieved. But actually, I collect my data and the interval of data wrong. So if I apply the proper approach, I will get these parameters. And then, as I explained during the training, the real better approach is to have each component's PDF and look on it to take some preventive actions. So now let's move to the last case of this training. So the last case is the case study 4 is about a valve. Is another equipment that's very used is very take influence in not only reliability but safety and system performance. So here we have the start dates. That's we implement all different valves. So here you can see that we have 4 different valves. So the valves are the same, have the same functions in the end from one vendor. So there I put all there together. Then now I consider the similar products, and then I got information from different components and have this date for each failures, repair time, when repair finish, and the maintenance, what type of maintenance, cause, consequence, and solution. So what I need to, the wrong approach again is to just start to get some interval of failures without look up on the type of component that failed. And that's similar that we had in the last case. So the proper approach is to organize data from each one of the components. So you can see I put first the actuators, second the gasket, third the diaphragm, in order to have the proper interval between failure. Then I will get this information here to predict and use my reliability prediction. To do that, again, I need to prepare a template for each component, such as actuator, gasket, diaphragm, and diaphragm. And then in the end, I will have this information. So now let's move to the Viable software and let's look how does it works. So since you already know how to open a file in a Viable Plus software, we already just put the template in here. So just assign to rename. So let's put a case study for valve 1. And I put in valve 1 because we got the data that we have, as we saw before, without considering, now we work on a valve without considering the components. So that is the generic usual database that we have. We need or even collect from files. Then we need to calculate the interval of failure. Then of course here in this template we do not have, let's assume that we do not have the information about the components, and we just get this value that we have here to calculate the interval of failure. And then of course we have small intervals that will always mostly force That's this PDF is a log normal one. That's many failures happen at the very beginning of life cycle. And that's not the reality we see later on. But let's consider as the first case. Let's put valve 1 in here. Valve 1, and let's just see what we've got from our goodness of instance test based on rank regression. So we have all the methods in here. We assess, and we have viable 3 parameters as a PDF and generalized gamma. Let's just implement to see what we've got from the viable 3 parameters. So here we have gamma negative, a negative value for gamma. So we are not going to use that. So we just want to assess, and again, just move for, let's say, maximal likelihood, and just assess the data. So we have gamma. Now we have viable 2 parameters. So let's implement that. They will come out with a generalized gamma. We want to use viable 2 parameters. So just observe the likelihood function here, values -23. Let's see if we have viable 2 parameters, what we've got. So we've probably get very approximate value for likelihood. We also get likelihood -23. The difference between the two, first and second best PDF, is very small. So I just use these viable 2 parameters, and here, based on the viable 2 parameters, we see that we have the small value of beta that's demonstrated as a log normal shape of the PDF, and we have the eta here. We have 60%. What is telling us that 60% of this valve failed in 1.2 years. Let's just plot the PDF to confirm what we saw in the parameters here, that we have a log normal. That's the failure. The PDF shape is skewed to the right side, and that means failure concentrates in the first year of operation. That's what we have from the PDF. So we skew it to the right side, and failures are concentrated in the first years of the failure. Okay, so let's now going to do the proper assessments by assessing each one of the components. So we open the folio in here, and we check which are the first component that we assess. So now what we're going to do is to get the data from the actuator. So here we come out a new folio, but we get what we want to do is to get first the time to failure of the actuator that we separated in this template here. Now we are organizing this template here to avoid this mistake, and then what we are doing is we are the first component is the actuator. So we have here we just rename, we put the case study for actuator, and then we paste the data here, paste the data here. Here we are, and then now we perform our goodness of fitness test, see what we've got. So we have a normal, the second one is generalized gamma. So we just implemented, and here we'll see the correlation coefficients of this PDF, but we want to apply the normal. So here there is issue with the Fisher matrix for the confidence method, but we don't want to assess the confidence method. So here we are, the generalized gamma, and the whole is 99.98. So let's take a look on the difference between the first one, the second one, that's a normal. So 99.98. So if we use a normal, we have here 98.11. That's also a very good approximation. And let's again use the generalized gamma and take a look on the profile of the PDF. That's very interesting to see the shape, and the shape probably will be something similar with the with the normal. So here we have, so let's come back in here. So just come back to use the normal PDF that we want to use. Here we are. Those are the normal PDF. Yeah, and then let's put here actuator. And then of course for an actuator we expect to have, and if it's electronic failure we expect to have some exponential PDF, but if it's normal there are some mechanical component that's failing and with 1.9 years in this standard deviation. We need to look on the root cause to understand that. But by the time, just look, actually we already know the PDF shape of such parameters, and then since we have normal, it's very simple. The assessment, we do not have surprise, we have very clear definition of the PDF. So here we see that the PDF is, we do not have, we have some time that's is before 0, but of course if we have that is what we've got if we plot the generalized gamma. So here we put PDF, and we can plot other functions such as the failure rates, and the failure rates will start to increase in the very beginning, so is what we expected. So as I mentioned, the failure rates start to begin in the failure rates start to increase in the very beginning, and we can look also in and plot also the reliability function. So here we want to plot the reliability function, and in years of course. So we need to change it here, so that now we have our reliability function of the actuator. Just correcting here. Here we are. Then of course we can plot the generalized gamma if you wanted to check, but let's consider that normal PDF is fine. It is for our data, and we need to investigate what we've got the normal PDF. So now we are adding another folio, and then we look on the first component and the gasket. The gasket, here we expect increasing failure rates, wear out, the time of component that we have wear out, and then we just add the folio, and then we make the assessment of this component. So here we are. We're waiting for the folio comes out, and then we are including this data that we plot in this gasket component. So here we are. We put the gasket data in here. We paste the date, and now we perform the goodness of fitness test based on Hunger regression to check which are the PDF that better fits on this data. What we have is generalized gamma is the gamma, is the one. So it's a little bit skewed for less and skewed for the left side, because this value here 1.31. So let's do just an exercise here. You see that's the best PDF is gamma. Let's just plot the graph. These are the parameters. That makes sense, of course. We have increasing failure rates, we have wear outs, but in real life we need to investigate why we have a failure in 1.36. Try to understand. So just be clear, the PDF format that we've got is here, skewed to the left. And let's see what's happening if we replace one data here. Let's say, for example, and that's a common case that we have. We do not have this failure happening in 136 year, in 1.3 years. And what is the effect of the PDF? So just getting this value here, the PDF will be totally different PDF for sure. So, and that's a very good understanding. For example, in the case that we have a small number of failures, that can be triggered, for example, that can explain some human error. That's the equipment fails some small period of time after the repair, and that is caused, that's not degradation as human error. So in order to predict the real performance of equipment, we need to take it out as human error and assess as well with human error to demonstrate the effect of human error in reliability. So here we are. Let's just make an assessment to see what it looks like now when you got out this point. So we have now the variable tree parameters. So just implement. So we see that we have different patterns of failures. So we have variable tree parameters. So let's see which are the values. So 1.3 now is skewed to the right side, but have a different pattern. So basic on the first data with 1.36 years of failure, we have this pattern here. If you take it out, this failure that can be triggered for human error, we'll get different pattern. So different, totally different. So that now is skewed to the other side, and we have different pattern of also concerning the reliability. It's totally different. So you can see that how one date can influence in your analysis, and we need to be careful if some failure are triggered by human error or wrong design when we want to assess the equipment reliability. So we just get this all the information. Let's come back to the previous, just to show that sometimes we need to clean out our data, assuming that some data are not correct, but that's not the case in here. So just let's come back and consider the normal PDF as the best PDF for this prediction here. So here we are, we have a normal PDF, and again we have the gumbo. Actually we had the gumbo. So let's run again the test to be sure that I'm doing the right. Let's see, the second was the second that I've got, was the first one that I've got. So it's gumbo, it's not normal, it's gumbo. Yeah, and just calculate the parameters. So it's a gumbo. Okay, just calculate the parameters. So, and then of course now I can calculate now my PDF, let's put the PDF gasket. And here is, I need to just to put the proper name. Gasket. And then of course I need to update in that. There's a PDF shape in here that's not correct. And move forward for the next component. So just update the failure, so that will be the opposite. Yeah, and now I insert one new. So I made a mistake here, just want the plot. It's not a data sheet. I can also insert data sheet and paste another date and compare both reliability. Can do a lot of information here. So now just put the reliability, plot the reliability. Actually, it's a very good reliability of the equipment concern this there is only one point that brings the reliability low, is that's this 1.36. But if we saw that if we eliminate that, we have very high reliability. But even though let's keep the data that we've got at the moment. That the objective here is not to assess actually the root cause of the failure, to take a decision of eliminating or not some data, but we need to be aware about that. In some cases we need to do that to have a better and accurate prediction of the reliability. And we saw in this case that we have influence on the data. So here we have our increased failure rates after the periods of 1 year, let's say, we are starting to have increasing failure rates. And that makes sense for the gasket. That's what we expect for the gasket component. So here we are. Now we move to the next component. And then in the end we have all the failures for different components. Now just clicking OK here. While it's coming the data, we get the next component, that is diaphragm. So now we got the data from diaphragm. That takes longer to fail. And let's see which are the PDF that fits well in this diaphragm. So now we create the last folio, case study for diaphragm. So here we are, we go to the template, we just copy and paste what we have in there. Now I'm pasting the data. Then we have the last component. Now we can paste the data here. So just have an issue here in the variable. Yeah, that's fine. Just click on the database that you want to work and paste. Now come out the information. Then we go through our rank regression analysis, goodness of fitness tests, consider the rank regression methods. And here is very simple. We just plot and we got the PDFs better represent this data is a variable. So we implement that and take a look on what these variable 3 parameters bring to us. So here will come out the parameters. Yeah, and then we have here 3 parameters of the variable. We have the gamma 3.5. That means until 3.5 we have 100% of reliability. Then the failures will happen after this 3.5 very fast. So you can see that 60% failure happen soon after this 3.5 years pass, and then this very concentrated in this let's say between 3.5 and 4.3 years. So that is the characteristic of log normal. So let's just put in here the proper name. This is diaphragm. Okay, now what we're going to do is to take a look on the PDF parameter. So the shape of the PDF, we expect to have some log normal, exactly log normal, but we have a range of is 3.5 years, and then the failures are concentrated between 3.5 and 4.3, as I mentioned before, and that is the PDF. Now what we want to plot, additionally we want to plot the reliability. So the graphic information gives us a very simple understanding about the patterns of failure, and that's why I always it's very good to use a software. You cannot get a conclusion only look on the parameters of the PDF. And then if you have a software like this Reliance software, you have very good resolution of the graph that enables you to have a clear picture of the pattern of the failure and the pattern of your reliability, of your failure rates, and then you can really work well and take better decisions. Use graphically also these functions that you define mathematically. So you need to have the background. You see here that the software, you need to click on the right button in the end to make the proper analysis. But of course, if you have this background, and this background you learn during all the models of the training, in the end, that will not, you have no issue to have a proper analysis of the data. And that's one of the most important points that we have actually in this training. So here we see the failure rate, how fast is increasing after 2.8 years, after 3.5 years. So that is the characteristic of this equipment diaphragm. And now what we're going to do is to create our last folio for now the valve, but consider different interval of failure and put all together. And then we compare with the valve one. So just like creating some new folio here, and now I put all these dates that we have in each one of components, actuator, gaskets, and diaphragm, and then I will use that for compare the two cases that I work and make assessment in the valve lab. So here we are just creating the folio. Now I rename for case study 4. Let's put valve 2. Now, rather than go one by one to copy, and I just come in my template, that is faster to do that. I go up, and now I need to get information from the right template. So the one that indicates that I have each equipment separately, that is the template. Here you can see organized by each component, the actuator, the gasket, and diaphragm one. Then I can get this search interval of failure and calculating there. So just making faster the assessment, just I will paste in here all this data and just come back in there, copy the proper template. That is this one that I have separated the component, actuator, gasket, diaphragm. I will copy and paste in my Excel sheets my viable software in here. Yeah, and then now I perform my, let's say, the goodness of fitness test. They demonstrate the Gumbo is the best PDF. I implement that. That is the information that I have concerning the valve. And now what I'm going to do is just to put here valve 2. I got the parameters. These actually in this case here that I'm doing now, I consider that now I want to assess the valve in the equipment level, before my lifetime data analysis equipment level, then I access the valve. But to get the proper interval of failure, I consider the, let's say, each component interval of failure. So that's why what I am doing. Then I got a Gumbo PDF. If I come in here and now plot the PDF for the valve, so I will see that makes sense. I have some failures. I will have the valve is a mechanical equipment with mechanical components. I will have a PDF that's concentrated some period of time. So here you can see concentrating in this period of time and a little bit skewed to the left side. So if I now I'm plotting the reliability, so that's the most important functions, and then I will compare in the case one that I did not have information. I assume that I did not have information about the components, and cannot see even the root cause. That's what each water specific component to make the correct reference of which time I will reduce from the date of the failure that I have. And then if I just assume the interval of failures, the mistake that I commit. So let's go step by step, just plotting the reliability of this function in years. And then let's put in here reliability valve 1. And let's put, it's valve 2 actually, to be honest. And this is valve 2. Let's put valve 2. Let's put here. This information also help when we compare two reliabilities. And then in multiplot that we already saw before, just put here the proper name, because make it also simple to identify that when you go for looking for this data. And then of course I will be able to here valve 2. Now what I want to do, just plot the failure rate and compare both cases of the valve, the reliability prediction based on valve level. But here consider the proper interval of failures, and in the other one, if I do not have information about such causes and which components, I will in the end make a mistake in my prediction, and then I can take a wrong solution. Similar what the previous case from that we assessed the screw compressor. So here I just put in hours. That's and I will see how is my failure rate function. Then I have just to come, and then you can see after 1 year, 1 point the failure is time really to increase. So I can establish this point to make inspection my valve. And then of course, if I look individual components, I will have the individual patterns of failure, and then need to pay attention. As much as information I have, the more organized the FRACAS, better I can do my prediction in the end. So now that we perform this analysis, let's just compare this case that I got the proper interval of failure with this case, the first case one that I just have no information and the level below which component failure, and then just get the interval of the dates of failure in the valve. And then to do that, we need again come to folio here, multifolio, and add overlay plots. Then when we do that, the software will ask which overlay plots we want to do. So here we see that we can compare different components. So I just want to compare the valve 2 with the valve 1. Then automatically come the graph of failure rates. And then now we have this different case. So the blue graph is the valve 2. You see the difference of reliability, and the valve 1 is the black one. So here we can see for a small period of time the black graph is higher than the blue graph, but for a majority period of time, just put in years here, we have that's the blue line is much better, have a higher reliability in time than the blue line. So in the end, that's take influence, very high influence in our reliability. So, for example, let's say that I want to assess, start some targets in 1.4. So in 1.4, the reliability of the valve 2, the second case that we will assess properly the, let's say the interval of failures. Let's consider 1 year to make it easier in 1 year here. So you can see X in 1 year we have 88.9, and here in 1 year I will have 40%. So in 1.4 year, here exactly in the first case that I assess without information about component and the cause of the failure, and just take the interval of failure between the dates of failure that I had to predict the reliability of the valve, I got 29% of reliability at 1.0. So if I have the targets of in this case 8.6 or 8.5, I will improve. But in the end, in reality, the proper reliability is this one, that's 8.65. I just got the wrong data here, make wrong calculation. So we need to pay attention that, and that's the influence from the let's say the database that we have. So let's take a look, compare now the failure rates. So we have the case, totally different patterns of failure rate. We have almost constant failure rates from the case 1 and increasing failure rates for the case 2. That's a different approach. So based on this first case approach, since I have almost constant failure rate, I will define some reliability to make inspection, and that forces me to make a lot of inspection. But based on the proper prediction, I will do inspection after 1.8 years or something around here to detect failure. And let's take a look on the PDF for these two different organizations. It's totally opposite. So the first one, because I just get the interval between the dates of the failure without looking at the components, the cause, I predict a log normal. But by getting the proper definition, I get a gamble. So here in one case, the failure are shifted to the failure are concentrated in the very beginning of the life cycle. That's not true. And in this case, I can even ask for a vendors, make the wrong decision here, considering that's early life, but actually it is not early life. So using correct the data and predict, have a good database, have a high influence in your reliability. Another important aspect when you are performing reliability analysis is the confidence level. So we have, by using software such as Viable, rules from Reliable Software, it's very simple to apply confidence level. So since we have the data, the software automatically calculates the Fisher matrix, for example, then we just need to define if you want two size of confidence level for each one of these plots and the level of confidence level. So when we apply that, we automatically get in our graphs the confidence level, and then we can make assessment concerning different confidence, similar confidence level or different patterns of reliability. In this graph, you can see here the upper limits and the lower limits for the best case for reliability prediction on the correct case, and here below we can see in the purple the upper and lower limits for a worst case, a wrong reliability prediction. And we can see that even if you get the worst case, the lower limits for the proper reliability compared with the best case of the wrong reliability, most of the time the reliability will be higher for the proper reliability prediction. So if you look on let's go to the equipment level. So here let's come back to the valve 2. We always predict we can predict different confidence level, and we see if depends on the confidence level, we have different influence in the lines. In some cases they will be more straight or not, depends what we are predicting here. Of course, depend the number of data as well. We have more narrow or deep, let's say, distance from the confidence level upper and lower confidence limits to the functions that we apply. And then, of course, just to have a reference, we can come also to calculator and define the calculator that we have in Viable software, the reliability, the confidence level. We can also calculate in that. So if you come in and here, we can define, for example, if you want to define the reliability for 1 year, usually we have one variable. But if you want to apply a confidence level, so we just to put here, in case of both sides, 9% of confidence level or even 95%. So we get our answer always in this two level of confidence level. So here, for example, we have the upper bounds and the lower bounds, the upper limit level and the lower level of the confidence concerning 95% of confidence level. So that means that if we have a target of reliability of 88% in 1.2 years, or even let's make simple now, in 1 year, 90% of reliability in 1 year, our reliability can come in 77% that will be acceptable, is still in the interval of 95%. And of course we're getting higher, but we need to be careful with that, because depends on the quantity of data that we have, we will have a lower value for our lower bounds of your confidence level. And then to use confidence level, we need to really need to be aware that depends on the level of the information that we have. Such confidence level will affect the prediction that we are performance as well as the target that we are defined. So we need to know very well about the equipment that we are predicting to use confidence level in our targets. So let's finish this model. So we get to the end of the model. Now, thanks for your attention. I hope that we stress these 4 case studies with all possibility and issues that you used to have in your reliability prediction for historical data that you have in your FRACAS or in other database. We highlight all the most important information. Then it's a matter of practice that you need to do now to get more familiar with this approach and to use in your daily routines to make predictions, to take decision for the time of inspection and to compare different equipment performance as I define here. Okay, so let's move to the next model.